Hello guys, it's me, Lorenzo Camacho, and I'll be doing my recorded presentation of my incomplete in Module 1, and I'm talking about this problem, which is the second problem in PS 1.1. This is Thornton and Marion problem 12-8, and it deals with the problem of a double pendulum, and I'm tasked with finding the characteristic frequencies as well as the describing the normal modes of the system. I will be describing the normal modes of the system using a graphical representation. So since this problem is quite long, I took the liberty of already writing down the positions of both M1 and M2 using polar coordinates. And then this part here, this part here is just writing down the components of the Lagrangian. So this is the kinetic energy. This part is skimmed very fast over if you're gonna look at the maybe solution manual of Thornton and Marion. So it goes directly here in the secular equation, but this is the derivation of the Lagrangian. So there are specific parts here that are important, specifically here where we have to apply small angle approximations to cancel out this term, because cosine of theta 1 plus theta 2, since theta 1 is approximately equal to theta 2, the sum of it is equal to 0. This should be difference. This should be the difference because it's cos sin. Yes. So this should be the difference. And then this is the whole kinetic energy term. And for the potential, again, we apply small angle approximations with the Taylor series of cosine theta. So we can get rid of this cosine term. So applying small angle approximations, we get this potential term, potential energy for Lagrangian. Our total Lagrangian is given by this, and since there's our Lagrangian is a function of theta 1 dot theta 2 dot, it has, and it's indirectly a function of t. It has 2 degrees of freedom. So likewise, we need two Euler-Lagrange equations. So they're given by these two, and now we have to express it in our typical simple harmonic differential equation. So we're gonna represent both of these equations in one equation using matrices. So if we put down here theta 1, theta 2, and if we have to look at our function here, we can represent this it's a matrix multiplication operation between the m vector and the theta vector. So if we look here, so theta 1 and theta 2, we can just write these coefficients 2ml squared and ml squared. So if you can see, if we multiply this row over this column, it results here, provided that this is differentiated twice with time. And then similarly, this is just the coefficients ml squared, and then our remaining terms are these without the L squared factor. So multiplying this out, this only has theta 1, so it's 2mgl, then 0. since there's no theta 2 component, and here it's just 0 mgl. Shouldn't have a... Okay. So now we're gonna be solving our secular equation. So where did this come from? This basically came from the operation of, we're gonna assume a solution of theta of t, a e I omega t, and then we're gonna differentiate that twice to get negative omega a e I, oh, it's supposed to be omega squared, omega t. So this is your, when it has, since in this part it's being differentiated twice, we're gonna result to having a coefficient of this. So as you can see here, that negative omega squared of a is not really necessary, but our negative omega squared is going to be attributed to this matrix, because this was differentiated twice. So okay, actually solving that now, maybe I'll just speed this up in post. Getting the determinant, we get that the square of the natural frequencies, which these are the actual natural frequencies, because if we square root these further, we get plus minus g over L times 2 plus minus square root of 2. And then the only valid natural frequencies are take, it's lagging, take only positive frequencies. There are no negative frequencies for the oscillations, so even if we square root these further, we're only taking the positives. So if we square root these, we're only getting, so omega 1 and 2 are positive square root of g over L 2 plus minus square root of 2. So these are the natural frequencies, or these are the frequencies, these are the eigen values to the eigen problem in coupled oscillations. But now to describe the normal modes of the system, we should also get our eigen vectors. So what we did is we solved this problem. And what H is a matrix such that when we multiply it to this difference, it equals 0. So basically, it's the, well, I'll discuss it later after we find H. So the way we find H is, So explaining this portion, what we did is we already solved our secular equation. We got our eigen values of omega 1 and omega 1 squared and omega 2 squared, and we just square root that to get our natural frequencies. But now we're trying to find our eigen vectors, and to do that we sub in our values of this again with our found eigen value squared, and then we let H be a two element column vector that we have to solve. So now we simplify this equation by factoring out MGL, and then we're left with these elements, and then it doesn't matter which row we multiply with this, so we just chose our top row. It just has to satisfy the equation of this vector multiplied with this vector is equal to 0. So this is just matrix multiplication, and then we're trying to find the ratio of H2 over H1, so we can find out the relative values of H2 and H1. So doing so yields the value of square root of 2. So for H1 is equal to 1, H2 has to be equal to, oh, it should be negative. This H2 should be negative square root of 2. And following the same procedure, because in this one we used omega 1 squared. So we use omega 1 squared for this this particular case, seen here. And now if you do the same process with omega sub 2 squared, you're gonna get H1 is equal to 1, H2 is equal to square root of 2. So what do we now do with this eigen vectors? So we have all of our components to derive the general solution for a double pendulum. So for the general solution, it takes the form of so this is the our general solution, where C1, C2, and gamma 1 and gamma 2 are dictated by, this is the I should write it down as well, angular velocities. So for now we're not going to be thinking about the angular velocities. We're always going to be assuming that they're coming from rest. So let's say assume theta 1 dot is always 0. Okay, because that's what I based my made simulation off of. So if we're gonna separate the general solutions, what we're gonna get is what we're gonna do is, for my purposes, what I did was we looked at, we're gonna assume some things. We're gonna assume that so at t is equal to 0, we're gonna our general solutions boils down to so normal modes can be described as linear, the specific orientations of our initial positions. So a certain configuration of my angular positions makes it so that the double pendulum exhibits a simple harmonic motion. If we set this, if you put a prefactor of square root of 2 here, we can eliminate the square root of 2. So, you see? So if we put a square root of 2 of theta O2 plus O1, so that gives us what? So if this was square root of 2 and we just add them together, we can cancel out our square root of 2 prefactor, or just the coefficient, and then this term would cancel, right? Because it's positive, negative. So we're left with 2 square root of 2 C1 cosine omega 1 t. So if you can recall, this is our square root of g over L 2 plus square root of 2. 2. So this is the higher of the angular frequencies. So between theta omega 1 and omega 2, omega 1 is higher. So this is our higher frequency. This is our higher frequency. Likewise, so presumably this is our asymmetric. Here we have square root of 2, following the same logic of trying to cancel out that square root of 2 coefficient. Square root of 2 of O2 minus square root of theta O1, excuse me, it would be 2 square root of 2 C2 cosine omega 2 of t. So as you can see here, omega 2 would be this term, except it's minus instead of plus. This would be our lower frequency. Lagging. And presumably this would be our symmetric mode. So why is this higher frequency? Why is this lower frequency? I think it's better to see in the simulation. And as for how I solved C1 and C2, you can derive a parametric equation, a pair of parametric equations that describe the relationship of C1 and C2 in terms of set initial conditions of theta 1, theta 01 and theta 02. So I doubt I made the 15-minute mark, so apologies if this is too long, but I think this is a little bit more comprehensive than the solution manual. So this is my double pendulum. So here I'm assuming this is actually wrong. It should be no, this is right. So okay, my initial conditions is it starts off at 45 degrees, square root of 2, because remember we're in our normal modes, the theta O2 has to have a coefficient of square root of 2 to cancel out that square root of 2. And then this one is, I put it as negative 45 degrees. So what we're doing is we're following lag. We're following this lower one, and if we're gonna simulate it, you can see that it's like a simple harmonic motion, It's more apparent if we make this smaller. So if you make this 15, so this is symmetric, as you can see, and it's more apparent when you see the, I'll make it 45 to make it more pronounced. So it's more, if you make this positive, which presumably again, which is our asymmetric mode, we can see that it is indeed asymmetric. And you can see just visually that it's moving a lot faster because this is our higher frequency. So I'll put the link to this simulation in the description below. And I think that's all I can say about the normal modes. Thank you for watching.